So this is a problem calculating the maximum stress for a given member or a bar. So let's look at the question. A cylindrical bar 60 mm diameter and 200 mm long is fixed at one end. At the free end it is loaded as shown in the figure with an axial load of 12 kN, a downward transfer load of 5 kN and a torque of 1.4 kN meter. Calculate the maximum stress at point P of the bar. Okay, we have a cylindrical bar of diameter 60 mm and it's 200 mm long, and it's fixed at one end just like cantilever beam. We have one end fixed or hinged. At the free end, I mean on the other end, I mean non-hinged part, it is loaded with an axial load of 12 kN and a downward transverse load, a load which is acting downward, a 5 kN. In addition to that, a 1.4 kN meter torque is also applying to this bar. So we have to find the stress at a point P of the bar. When you look at the figure, you can understand where is this point P. So we have to find that maximum stress at the point P. So this is the given diagram for this question. 5 kN acting downward, 12 kN axial load and 1.4 kN meter torque. Okay, you can see at the point P, which is at the lower end part, we have to find the maximum stress at that point P. That is our aim of this question. So let's look at each step how to solve this problem. First of all, just write the given condition. Axial load we have to convert into Newton. We have given in kilonewton, you have to convert into Newton, 12 into 10 raised to 3 Newton. Then bending load 5 kilonewton, 500 10 raised to 3 Newton, and torque, let it be MT, capital MT, and 1.4 kilonewton meter, right? So first of all, that kilonewton should be converted into Newton into 10 raised to 3. In addition to that, meter should be converted into mm. So another 10 raised to 3. So 1.4 into 10 raised to 3 into 10 raised to 3 Newton mm. Then diameter and length. You have to find the maximum stress at the point B. The very first step is to find the area of the bar. Area of the bar, you know, it's a circular cross section area. So pi d square by 4. So the area will be 2826 mm square. Then there is axial load and bending load. First of all, due to axial load, there will be a tensile stress will be developed due to the axial load, which is of the formula symboling P by A. P is the force applied. So force is 12 kilonewton. So now to convert into Newton, 12 into 10 raised to 3 by area. So the tensile stress is plus 4.246 Newton per mm square. The positive sign is due to tensile stress. Okay, for when you solve this problem for in stress, tension or tensile stress is considered as positive, while the compressive is considered as negative. So tensile stress due to axial load is plus 4.24 Newton per mm square. So we have found out the tensile stress. Next we have to find the bending stress, right? Bending stress is caused by that 5 kilonewton force from the towards the downward direction, which causes a bending. So bending stress is find by the formula mb by z. Mb is the moment due to that bending force. 5 kilonewton is the force that caused the momentum or bending momentum. So 5 into 10 raised to 3, now it's in Newton, into that whole length. Okay, it is turning about that hinged point, right? So I have to take the whole distance 200 mm. 5 into 10 raised to 3 into 200, I get 1 into 10 raised to 6 Newton mm. That is the section modulus for a circular cross section. It is pi d cube by 32. So finally 21,205.75 mm cube as section modulus, and bending stress is minus 47.15 Newton per mm square, and the negative sign is due to compressive stress. So we have to find the net effective stress, which can be due to this tensile stress as well as compressive stress. So final net stress at the point P is minus 42.90 4 Newton per mm square. So now I got sigma x, right? In the x direction, sigma x has minus 42.904. Next is the shear stress due to the torque. We are applying a torsional load, right? So now to find the shear stress, we have to take the maximum shear stress equation, because the point to be determined is at the outer diameter, which is the maximum possible distance from the neutral axis. So its formula is 16 into mt by pi d cube. 16 into that 1.4 into 10 raised to 6 by pi into 60 cube. So finally that shear stress is 33 Newton per mm square. So writing down all the value, the state of stress at the point P is sigma x. Okay, that sigma x can be due to both tensile and compressive. Okay, so that sigma x as effective sigma x as minus 42.904 Newton per mm square, and there will not be any sigma y in this type of question. Okay, sigma y is 0, because the point to be determined at the exact outside. Okay, there will be only sigma x, and tau xy is 33 Newton per mm square, and we are asked to find the maximum principal stress at the point P. So there are two principal stresses, sigma 1 and sigma 2. Okay, the only difference between both is the sign convention, that both term is separated by one having positive sign and other having negative sign. So in order to get the maximum value, you have to take the equation contain the positive sign. That means half of sigma x plus sigma y plus root of sigma x minus sigma y the whole square plus 4 tau square xy. On the other hand, the equation will be having negative in the middle term, which would be having less value compared to this term. So among the two equation, this is the one having maximum value. So the maximum principal stress at the P should be find by using this formula. So the final answer will be 17.91 Newton per mm square, which is the maximum principal stress developed at the point P. Okay.